Good day, students. Welcome to Mathgotserved.com, where we don't just solve, we teach. In this clip, we're going to be going over problems 25 to 28 of the Geometry Common Core Regents exam for January 2016. All right, let's take a look at question 25. It reads, triangle ABC is graphed on the set of axes below. So you can see triangle ABC. Graph and label triangle A prime, B prime, C prime, the image of ABC after a reflection over the line x equals 1. So one thing you want to note concerning line reflections is that when you're reflecting a geometric figure across a line, what you do is you can just use the vertices, okay? All you do is you reflect the vertices in the same distance in the direction opposite of where the actual or object is across the line, okay? So in this case right here, we have the triangle ABC. Our line of reflection is x equals 1. So what does that line look like? This is a red line right here. Most students look at the x-axis and they say, oh, you know what, since the x-axis goes side to side, x equals 1 is going to go in that direction. Well, that's not the case. The x-axis is actually a y line. This line is y equals 0, okay? The y-axis is an x line, it's x equals 0. So whenever you have x equals a constant, it's going to be a vertical line, okay? So when x is equal to 1, you want to draw the collection of points where x is always 1, which is the vertical line that I just sketched. Okay, so this vertical line is the line of reflection. The original object is to the left of our mirror, okay? So if you stand to the left of a mirror, where does your image get reflected into? Your image gets reflected into the mirror to the right of the surface, right? So if this is our object right here, it's moving all over the place. We're going to reflect it to the right, okay? So let the vertices be your guide here. So this vertex B, is 1 unit to the left of the line of reflection. So its image is going to be 1 unit to the right. That will be B prime. Okay, let's change colors here. So B prime under this transformation gets mapped here. C prime 1 unit to the left. C is 1 unit to the left, so C prime will be 1 unit to the right. A is 1, 2, 3, 4 units to the left, so A prime will be 1, 2, 3, 4 units to the right. Okay, so this is a triangle that we're talking about the image of triangle ABC. Okay, so all you just have to do is draw the triangle and you are in good shape. Now, one thing you want to keep in mind is do not forget to label the vertices, okay, of your triangle accordingly. If it's not properly labeled, you could lose points. So just make sure that you sketch the image under the reflection along, let's even write the equation of the line, x equals 1, and then label your image correctly. All right, let's take a look at question 26. It reads, in the diagram below of circle O, with diameter BC and radius OA, chord DC is parallel to chord BA. Question. If measure of angle BCD is 30 degrees, determine and state the measure of triangle AOB. Okay, so let's go ahead and annotate our diagram based on information given. The label that I'm going to place on the graph, just one of them, is the fact that DC is parallel to BA. So DC, the segment is parallel to BA. All right, something to recall concerning parallel lines and transversals. Whenever you have two parallel lines cut by a transversal, the alternate interior angles are congruent. All right, so to help us solve this problem to find measure of triangle AOB, I'm going to solve this problem using a two-column proof format, okay? On the Regents exam, you do not have to do what I'm doing right now. You could do it with much fewer steps, but what I'm trying to do is I want to show you exactly what is going on in the problem solving process, okay? So we have our statement and our reasons. Okay, so first statement we're gonna consider is the fact that DC, segment DC is parallel to segment BA, and that's a given, okay? Now, if you have two parallel lines cut by transversal, I mentioned it earlier, you have, this region right here between the two parallel lines is known as your interior, okay? And cool things happen with the interior angles, depending on how you group them. One of the cool conclusions you can arrive at is that the alternate interior angles, this angle, angle C and angle B, are alternate interior angles, and they are congruent, okay? So let's go ahead and write that down. Angle C is congruent to angle B because in this scenario, alternate interior angles are congruent when you have two parallel lines cut by a transversal. Okay. What else do we know? We were told initially that measure of angle BCD is 30 degrees. So let's go ahead and write that down. The measure of angle C is 30 degrees. That's also another given. Okay. So what conclusion can we draw concerning the measure of angle B or ABC? Measure of angle B is also 30 degrees, okay? And we can just, since these two are congruent, we can just write by substitution here, substitution. Just take the value, since measure of angle C is 30 and angle C is equal to angle B, you can just put angle B here and then get 30 degrees. Okay, so what else can we deduce from the information that is given? Well, we are told that BC and OA are the radius of the circle, okay? So if BC is the radius and OA is the radius, we know that all radii are congruent, okay? So BC, well, BC is the diameter, OA is a radius, okay? Right there. Now, what's the relationship between BC and OB? Okay, BC is the diameter, so OB is half of the diameter, which is the radius. Okay, so if AO or OA is a radius, guess what? OB is the radius also. This is also a radius. So let's go ahead and write down some pieces of information. We know that BC is the diameter. Segment BC is a diameter. That's given. And then we can conclude that OC, actually OB, is a radius, one of the radii. It's a radius because the reason is half of the diameter is equal to the radius, okay? And OB is half of the entire length of BC. Now, since OB is a radius and OA is a radius, what can we conclude? We can conclude that OB is congruent to OA. What's the reason? The radii of a circle are what? Are congruent. Okay, all radii of the same circle are congruent. All right, now, what does that tell us about triangle OAB? If OB is congruent to OA, then there's a special designation, a special name that this triangle has, and that is an isosceles triangle, okay? So triangle OAB is isosceles. Why is that? Because base angles are congruent, okay? well, actually, we have a pair of parallel sides. Let me change my reason right here. Reason is one pair of parallel sides. We have one pair of parallel sides. Okay, we're going to talk about base angles in a second. I kind of jumped ahead of myself. Okay, now what do we know about the angles in a triangle? They add up to what? Let's go ahead and write down an equation. We know that the measure of angle B plus the measure of angle A plus the measure of angle AOB has to equal 1. So this angle is congruent to this angle, okay? This angle plus this angle plus this angle right here, all of them add up to what? They add up to 180, okay, by the triangle angle sum theorem. So they add up to 180 by the triangle angle sum theorem. Now, what else can we deduce? Well, since this is an isosceles triangle, these two angles are congruent. I indicated that earlier. So measure of angle A is equal to measure of angle B, and the reason is they're because of their base angles of what type of triangle? Of an isosceles triangle. Okay, measure of angle A is equal to measure of angle B. So since measure of angle B is 30 degrees, it just follows that measure of angle A is also 30 degrees, and this is by substitution. All right, so we have that's 30, this is 30 right here, and this is 30 right here also. Now, what's the measure of angle AOB? Well, let's put everything together and then we can see what it is. So angle B is 30 plus angle A is 30 plus measure of angle AOB, what we're looking for, equals 180. And this is simply by substitution. You substituted the measures of angle A and B into the triangle angle sum equation, okay? All right, now we just use algebra to isolate the measure of angle AOB and we'll be good to go, okay? So let's combine these two first. 60 plus the measure of angle AOB equals 180. That's addition property of equality. And then we can subtract 60 from both sides. And then we end up with the measure of angle AOB as 80 minus 1 minus 60, sorry, is 120 degrees using the subtraction property of equality. Okay, so there goes your final answer. Measure of angle AOB is equal to 120 degrees. Now on the Regents exam, you weren't asked to do a two-column proof. I just wanted to show you a model as to how to construct a two-column proof and also let you see the thought process behind the results that I am getting. Okay. All right, let's take a look at question 27. It says a directed line segment PT has endpoints whose coordinates are P negative 2, 1 and T 4, 7. Determine the coordinates of point J that divides the segment in the ratio 2 to 1. All right, so a tip for dividing segments by a ratio. When you're splitting a segment using a ratio, it's always beneficial to split your segment into vertical and horizontal components and then divide those components respectively to determine what the coordinates of the division would result in, okay? So to help us with this problem, let's give ourselves a visual, okay? You could solve this problem without the visual, but it's really helpful to give yourself a visual so you don't get confused. All right, so let's graph the endpoints. We're going to graph P first. P is negative 2, 1, 1, 2, negative 2, 1. That's the left point. And the other point, T is 4, 7. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7. Right there. All right, so these are the endpoints of the segment that we're going to be divvying up using the ratio 2 to 1. So there goes your segment right there. Okay, now these are the steps we're going to be using to solve the problem. Number one, we already did, which is to sketch the segment. Give yourself a nice little visual there. Number two, let's find a vertical and horizontal lengths. Okay, so we want to do a section by section consideration of this scenario here. So what is the run or the width, the horizontal span of this graph from here to here? How long is that? So let's write it down, the horizontal length. This is in the direction of our x-axis, okay? So the horizontal length is basically given by the change in x. So the horizontal length is going to be 4, how long is it from -2 to 4 is basically 4 minus -2, which is 6. If you don't want to use arithmetic, you can just count from here. 1, 2, 3, 4, 5, 6. So that's your run. Okay. Now, what's your rise? What is the vertical distance of the graph? What is that? So we're looking for the distance from here. Let me put this from here all the way to the top. What's the rise? How long is that? Okay. So let's write it down. Vertical length. Vertical length. That's along the y. How long is it? Well, we can just subtract the y coordinates, right? So we can do y2 minus y1. So we're going to do 7 minus 1, which is 6. Okay, so another way you can do it, just count the points. 1, 2, 3, 4, 5, 6, and then there you have it. All right, so let's write down the formula. Horizontal length, we did x2 minus x1. That's your run in the slope formula. And then for vertical length, we did y2 minus y1. You can use this formula or you can just count. All right, now we have the lengths of each segment. This one is 6, and that's 6. We're going to divvy them up in the ratio 2 to 1. Okay, I know some of you can already visualize what the answer is, because if you break 6 into 3 parts, you have 2 in each part, and then when you have the first 2 against the last one, you have the ratio there. Okay, so let me show you how to do it. First of all, we're gonna go to step 3, which is to determine the division ratio. Okay, division ratio. I'm gonna write it as a fraction. So it's 2 to 1. So how do we split it? The smaller part, the longer part, sorry, is going to be 2 over 2 plus 1, which is 2/3. So the 2 part will be 2/3 and the other part will be 1/3. Okay, so this is a division ratio that we're going to use to determine the longer part. Now that we're done, we're going to apply it to the entire length. So this 2/3 will tell me how to split it. Okay, the 2/3 will be the first part, and then 1/3 will be the last part, reflecting that 2 to 1 division ratio. Okay, so let's apply this division ratio to our coordinates. Okay. Now, for x, the horizontal length, we're going to have, we're going to calculate 2/3 of the entire length, 2/3 of 6, and it's going to be multiply this, that's 12 over 3. 12 over 3 is 4. And for our y coordinate, the same thing, we're taking 2/3 of the entire length, the vertical length, which is 6, and then we get the same answer, 12/3, which is 4. Okay, so the longer segment when divided in the ratio 2 to 1 is going to be 4, and then the shorter segment is going to be 2 units long because they add up to 6. Okay, so what are the coordinates going to be? Starting from P, we're going to go 4 units up and 4 units to the right. So let's write down what the coordinate is going to, the final coordinate is going to be. So starting from the point negative 2, 1, we're going to add on 4 to the x, okay, and 4 to the y, because that's the bigger section of our division ratio, 2 to 1. So if you carry out the addition, you're going to have 2, 1 plus 4, 5. So this takes us to point J, okay? If you don't like adding, what you can do this visually. So since you're going, we're going to split it 4 units for the bigger segment. You can start from here and just count. Okay, horizontally, I'm going to go 1, 2, 3, 4. And then vertically, I'm going to go 1, 2, 3, 4. Bam, there goes your final answer. Coordinates are going to be 2, 1, 2, 3, 4, 5, 5. So the point J that we're looking for is 2 and 5. So if you like using the graph to carry your computations, that's fine. I like to do it both ways so that you can see them reflected in 2 formats and you can pick the one that you like the best. So our answer is point J is 2, 5. All right, let's take a look at question 28. It says, as graphed on the set of axes below, triangle A prime, B prime, C prime is the image of triangle ABC after a sequence of transformations. So this is the original right here. And then after a sequence of transformations, you end up with the image right here. All right. So question, is triangle A prime, B prime, C prime congruent to triangle ABC? Use the properties of rigid motion to explain your answer. So the question is the sequence of transformations here an isometry? That's what it's asking. Where the lengths of the dimensions of this original figure preserved under the transformations that happened. So in order to answer this, we can just observe, take a look at these two figures. Okay, do they look identical? They certainly do. The shapes look unchanged, right? So what sequence of transformations do you think will take us from this, from the original here to the image? What sequence of transformations? Well, if you take a look at the B, you notice that B is to the right of A here, and B is to the left, B prime is to the left of A prime here. So what transformation does that call to mind? A reflection. It looks as though this original image, this original object was reflected about the y-axis. Okay, so we have one, a reflection. And then two, what do you notice about C and C prime? B and B prime and A prime? It looks like there has been a shift. How many units? 1, 2, 3. 3 units downward shift. Okay, so there's a reflection and there was a translation. These two transformations are isometries. Okay, so since you're isometries, guess what? The transformation, the composition of both of them is also an isometry, hence the dimensions are preserved. A prime, B prime, C prime is in fact congruent to ABC. Okay, so we can just write that down and we're good to go. But what I want to do is I want to do a real quick review on composite transformations, a composition of transformations. Okay, so we talked about the reflection here along the line y equals x. So we have a formula for that. A reflection along the x-axis, the y-axis I meant to say, not y equals x. The reflection along the y-axis, you use this formula right here. That's a formula for reflection along the y-axis. You simply negate your x coordinate, and then we had a translation downwards. So we're going to use this translation formula here too. Okay. So our first transformation is a reflection, and then our second transformation is the translation. Okay, so remember what I'm doing is I just want to verify that our conclusion is in fact true. On the Regents exam, you can basically state the transformations that took place, and then you can conclude that they're congruent based on the isometric nature of the two transformations, okay? But what I'm doing now is just a real quick review on how to carry out composite transformations. Okay, so in this problem, we have a transformation that's a composition of a translation. Well, actually, you reflect first and then you translate, right? So whenever you're writing down your composite transformation or composition of transformations, you write the last transformation first and the first transformation last. Okay, there are only two here, so we're going to go, the translation was last, so write it first, t 0, -3 on xy. This basically reflects, this is a shift 3 units down, okay? And then we're composing it with r of the y-axis, okay? Reflection about the y-axis. Oh, stop, just erase my homework. Reflected about the y-axis. So let's rewrite what I just talked about. So this transformation right here, the first one, is a translation 3 units down. And then this one right here, oh, okay, I'll put my coordinates, I want to forget that, of xy, is a, this is the first transformation actually. This is a reflection across the y-axis. All right, so what I'm going to do is I'm going to write down what the coordinates look like when you carry out these two transformations, okay? So for this one right here, the transformation 3 units down just basically involves adding nothing to the x and subtracting 3 from the y. That composed with the reflection about the y-axis. If you look at, we have the formulas here. So the reflection, which one did I just do? I did translation. So for translation, whatever the coordinates are, that's what you add to the x and the y. So the a and b, this is a and this is b. And then for the reflection formula, you just negate your x, okay? So this becomes negative x comma y. Now, if you compose these two transformations together, what we're going to have is starting from negative x, you do negation of x, and then you add 0, that's for the x coordinate. For the y remains unchanged, and then you subtract 3, okay? So this is our transformation right here. In simplified form, you're going to have negative x plus 0 comma y minus 3. Now let's test 2 points just to show that this transformation, this composite transformation we have here are in fact correct, okay? We're going to look at a and b. So a is 3, 4, b is 4, 2. We're going to carry out the transformation here and see if it takes us to a prime, which is negative 3, 1, and b prime, which is negative 4, negative 1, okay? If it does that, then we know that our what we said earlier is in fact correct. So let's go ahead and do it. Starting with point A, A is 3, 4, and we want to go to A prime. To do that, we simply take the opposite of the x coordinate, add 0 to that, and then take the y coordinate, subtract 3. Okay, this is a reflection. Reflection across the y-axis and then a shift downwards. That takes us to negative 3, 1. Negative minus 3 plus 0 is negative 3. 4 minus 3 is 1. And then b, 4, 2. If we carry out our composite transformation on b, that takes us to b prime. So you're going to take negative 4, that opposite of the x coordinate, add 0. And then you subtract 3 from the y coordinate, so 2 minus 3. So if you do your calculations, you end up with -4, -1. So are those the points for A prime, B prime? Yes, they are. Check, check. Okay, so this shows that what we stated earlier is in fact true. Now let's go ahead and write down the explanation of the fact that the image is actually congruent to the object. Okay, so the question was, let's go back to the question. Is triangle A prime, B prime, C prime congruent to ABC? And using rigid motion, explain why. So the answer is yes. Triangle A prime, B prime, C prime is congruent to triangle ABC. Okay, so first of all, say yes. Next is the reason. The reason is that the sequence of transformations, also known as a composite transformation, the sequence of transformations comprise or made up of, what was the first transformation? The first transformation was a reflection, right? Comprised of a reflection and then what? And then a translation. Okay, what do we know about these two transformations? Both of which are isometries. Okay, so what do we know about the composition of isometries? Is isometric too. Okay, so since the composition or a sequence of isometries, since the composition of isometries is an isometry because you're not changing the dimensions, okay, is an isometry, the dimensions are what? The dimensions are preserved under these transformations. Under these transformations, conclusion, hence, the image triangle A prime, B prime, C prime is congruent to the original. Okay, so anytime you have an isometric transformation, there is always congruency. Okay, so that's that. Thanks so much for taking the time to watch this presentation. We really appreciate it. If you found the contents of this tutorial helpful in your preparation for the upcoming Regents exam, do give us a thumbs up. Your positive feedback is very valuable to us. If you have any questions, don't forget to just include your questions in the comment section below, and we'll be glad to support you. Don't forget to subscribe, and more clips can be found on Mathgotserved.com. Thanks again for watching, and have a wonderful day.